Hello guys, welcome to my video. So today I'm going to be solving the October-November 2017 question paper 1-2 for physics, and the question paper is 1 hour 15 minutes long. And we're going to be going through some of the questions and how they worked out, and I'm going to try and explain every concept in detail. But if you have a particular question that you're interested in, I'd highly recommend that you check out my timestamps in my description below, or you just skip the video to that particular part that you want. I've put time codes so that you can be able to access different parts of the video that you're interested in. So thank you very much for the support. Please like, comment, share, and subscribe to my channel if you find the content interesting. Okay, so let's begin. So our keyword here is the word not, right? So let's first start with the first one, right? For the first one, it's ms to the power of -2, right? And for Newton, right, for this one, Newton per kg, Newton is actually kg ms to the power of -2 multiplied per kg. That would therefore be ms to the power of -2. So they are the same. It can't be A. Moving on to B. B is saying kg. Okay, so it's kg ms to the power of -2 multiplied by s, which is kg, okay, ms to the power of negative, okay, to the power of -1, right? But already here we're given again kg ms to the power of -1. So, right, we're already given kg ms to the power of -1, so it cannot, okay, be B, right? Moving on to C. We've been given Pascal, okay? So Pascal is actually kg m to the power of -1 s to the power of -2, because Pascal is the force per unit area, right? If you calculate force over area, you'll be able to get the unit for Pascal, which is that. And here we've already been given Newton meter. Newton meter is basically kg, okay, kg ms to the power of -2 multiplied by kg m, okay, so that's m to the power of -2, right? So that would be kg m to the power of -2, so it's kg, right, m to the power of 1 minus 2 s to the power of -2. That's kg m to the power of -1 s to the power of -2. It can't be C, so the left logical answer is D. Why is that so? Because Vm to the power of -1, that's basically the units for voltage, is the work done per unit charge, which is kg m squared s to the power of -3 a to the power of -1 multiplied by m to the power of -2. This goes away, so we'll be left with basically, okay, we'll be left with let's see, that's kg s to the power of -3 a to the power of -1, right? And for the other one is just kn is kg ms to the power of -2. C is charge, which is as, which is a, okay, s to the power of -1, right? So all of that to the power of -1, right? So it's as to the power of -1, okay? So that's going to give us kg m, okay, s to the power of negative, that's -3, and a to the power of -1, right? But that is not the same, because this one is m to the power of 2, right? So the answer has to be D. Move on to question number 2. What is the vertical component of this displacement vector? Okay, so if this displacement vector, which is 5, right? So we want to find the vertical component. What is the vertical component? The vertical component is the component in this direction, right? So if we're to create our triangle, this is basically for this angle theta, which is over there. If we're to extrapolate it to this side, this is the opposite, right? And this is the hypotenuse. So we apply the the sine rule, right? Or the Chashu tau. And that is the opposite, right? So we apply the sine. We know that sine theta, okay, is basically the opposite divided by the hypotenuse, okay? So our opposite is basically going to be, okay, so for this one, our opposite is going to be the hypotenuse multiplied by sine of theta, okay? So it's going to be 5 multiplied by sine of 37, right? So it's 5 sine of 37, and that's going to give us 3.0 kilometers, right, which is going to be A. That's going to give us 3.0 kilometers, which is going to be A. Okay, move on to question 3. The units of specific capacity, we've been given them to be kg to the power of -1, k to the power of -1. What are the SI base units of specific capacity? So basically we've been given J, okay, so for this question, we've been given J kg to the power of -1, okay, so J kg to the power of -1, and k to the power of -1. But J is basically joules, right? Which is kg m squared s to the power of -2 multiplied by kg to the power of -1 multiplied by k to the power of -1. But why is joule actually kg m squared to the power of -2? Well, we can look at it from the point of work done, right? We know that work done is actually force multiplied by distance, but force is mass multiplied by acceleration multiplied by that distance. Mass is kg, acceleration is ms to the power of -2, distance is actually m, so that would be kg m squared s to the power of -2. So in case you're wondering, where is kg m squared s to the power of -2 coming from? Because of joule, the unit for work done, that would be that expression. Okay, so if you go back here, this is going to be kg, okay, to the power of 0, m squared s to the power of -2, k to the power of -1. So it's going to give us m squared s to the power of -2, k to the power of -1, right? M squared s to the power of -2, k to the power of -1. The answer is going to be C. Move on to question number 4. We're given y px over q squared. What is the percentage uncertainty in y? Right. So for this question, we apply the laws of how we can be able to find percentage uncertainty, right? So it's a very important it's a very important concept that you need to know. So whenever we talk of percentage uncertainty, always make that thing the subject of the formula. So basically, y is now already the subject of the formula. It's px divided by q squared. Okay, so the percentage uncertainty in y will be equal to the percentage uncertainty in p plus the percentage uncertainty in x plus the percentage uncertainty in q multiplied by 2. Okay, so the percentage uncertainty in p, that's 6, plus in x, that's 2, plus in q, that's 4 by 2. Okay, so that's 6 plus 2 plus 8. That's going to give us a total of 16%. So our answer is going to be D. Move on to question number 4. Question number 5. A transmitter emits a pulse of electromagnetic waves towards a reflector. Okay, the pulse is reflected and it returns back to the transmitter. A detector is located at the transmitter. The emitted pulse and the reflected pulse are displayed on this cathode ray oscilloscope. The pulse takes 6.3 microseconds to travel from the transmitter to the reflector. What is the time-base setting of the CRO? So basically, we know that period, okay, for a CRO, we know that period is equivalent to the number of divisions, okay, the number of divisions multiplied by the time-base setting, multiplied by the time-base setting. So basically, that is what period is. How many divisions do you have? And you multiply that by the time-base setting that you have for that specific instrument that you'll be dealing with. So when you consider this one, right? A transmitter emits a pulse of EMF. The pulse is reflected and it returns to the transmitter. So let's assume you have a transmitter over here, right? And this is our reflector. So we put our reflector over here, right? So this is our reflector, okay? So our reflector is over here and we want to determine this that will happen, right? So the emitted pulse and the reflected pulse. So this is the emitted pulse. So if this is our transmitter and it's going to return to the transmitter, the detector is actually here. So this is where, according to the question, this is where we also have our detector, which is going to detect that pulse itself, okay? So the emitted pulse and the reflected pulse are actually shown. So this is the emitted pulse and this is the reflected pulse. So it's going to emit a pulse. So as it emits a pulse, we'll see this pulse being formed. As that travels and as that is reflected and it comes back, right, we're going to see again this pulse when it arrives at this position, right? So this is when it is actually reflected back, okay? Then we'll detect it again, right? But if it takes 6.3 to travel from the transmitter to the reflector, the period is the time taken from this point to arrive to that point. It has to be double, right? Because if it takes 6.3 to go here, okay, it's going to take again 6.3 to come there. So our period is actually 6.3 micro is times 10 to the power of -6, as you can see on the right. Those are the prefixes that you need in AS, right? Then you multiply this by 2. What are the divisions? This is 1, okay, that's 2, that's 3. So you basically have 3 divisions multiplied by the time-base setting, okay? So our time-base setting is basically going to be 6.3 times 10 to the power of negative 6. Okay, so it's 6.3 times 10 to the power of negative 6 multiplied by that 2 divided by 3. Okay, so it's to the power of negative 6 multiplied by 2 divided by 3, which is going to be 4.2 times 10 to the power of negative 6, or 4.2 microseconds per centimeter, which is going to be C. Okay, I hope it made sense. Move on to question 6. A hot air balloon is moving vertically upwards. So that's a hot air balloon, as you can see over there. And we're told that it's moving vertically upwards at a speed of 3 meters per second. So it's moving up. As it is moving up, it's moving up with a speed of 3 meters per second. A sandbag is dropped from the balloon, right? So the balloon reaches a certain point. Now when it's at that point, but if you agree with me here, right, this is basically our hot air balloon, right? That's our sandbag, right? So sandbag is going to fall down, okay? And it's taking 5 seconds for the sandbag to fall to the ground. So basically this is the ground, okay? So this is the ground, and it's going to take 5 seconds for it to fall from here up until it reaches the ground. So it will fall from here up until it reaches there. That's going to take roughly about 5 seconds, right? And want to find the height of the balloon when the sandbag was released. So let's consider the sandbag for starters. It's going to have, since it was already moving up, right? Since this balloon was moving up, this 3 meters per second is going to be pointing up, right? So it's going to be pointing up because initially it was moving up, right? So the 3 meters, okay, per second initially will be pointing up. As it points up, then it will start falling down. But it's going to start with 3 meters per second pointing up because we're told that it's moving vertically upwards, okay? But we know that S is ut plus half at squared, right? And we know that down is actually negative g, right? So we're going to say S is equivalent to 3 times 5, which is the time that it takes, subtract 1/2 times 9.81, okay? 1/2 times 9.81, okay? Multiplied by the time again that it takes, which will be 5 squared, okay? And if you compute this, it's going to give you an answer of negative 107.625, which is basically negative 108 meters, right? We're not really much interested in the sign, but I'm mainly interested in this value of 108, right? So the answer for 6 is going to be a B. So very important. It was moving up. So the initial one was not down. It was actually pointing up because it's moving up at 3 meters per second. Then the value of T we have, G is always negative 9.81 pointing down. Then we can find the value of our height. Move on to question 7. The velocity time graph for a train starting at one station and stopping at one station is shown. So we have a train starting at one station and stopping at the next station. Another train has double the acceleration, okay, double the acceleration, but the same maximum speed and the same deceleration, okay? So it is the same maximum speed, the same deceleration, and the same acceleration, right? Okay, but it's just double. Also, it is double the acceleration, same maximum speed, and same deceleration. So same maximum speed meaning that this, okay, so let's eliminate using the maximum speed. This should be one box. So it's one box, one box. Yeah, so both of agree with the same speed criteria, okay? Double the gradient, double the acceleration actually means, since acceleration, the gradient, okay, since the gradient of a velocity time graph represents acceleration, it basically means that we have double, okay, we have double the gradient, okay? So this gradient has to be double. If it was occupying 4 boxes, it now needs to occupy 2. So here it occupies 2, that's correct. Occupies 2, that's correct. Occupies 2, that's correct. Occupies 2, that's correct. So we can't use that for elimination. What else can we use? Well, since it's going to start at one station, right? So our train, let's assume here, it's going to start at station A. Okay, this is station A, and it's going to start at station B, right? Okay, so you have to agree with me that the distance from station A to station B has to be the same. It doesn't matter if you have double the acceleration, double the maximum speed, it doesn't matter. But the distance that you travel has to be the same. So I can use the area underneath the graph to determine are these things actually going to agree with each other. Okay, so let's start with the first one, right? We know that for me to find the area, this is a trapezium. Area of a trapezium is usually, okay, half A plus B multiplied by H, right? Which is going to be 1/2. What is my value of A? It's 1, 2, 3, 4, 5, right? So it's 5 plus, okay, right, plus 11, okay, multiplied by the height, which is 1, 2, 3, 4, 5, 6, 7, 8, right? Multiplied by 8. So if we compute this, we're going to find the area underneath this graph so that, you know, it becomes equivalent to, okay, it becomes equivalent to 64 meters, right? Meaning that from station A to station B, one station from the other, it's actually 64 meters. So if you find the area underneath these graphs, and if they don't add up to 64, it means that is not the correct answer. So let's start here, right? If we start here, it's 1/2, right? 1/2 A plus B multiplied by H. So it's 1/2. The value of A, okay, that's still 2, 4, 5. That's still 5, right? Plus, that's still, you know, 2, 4, 6, 8, 9, plus 9 multiplied by the same height, right, which is still 2, 4, 6, 8, which is still 8, right? So already this is wrong because I had 11 in the first one, but now I have a 5 and a 9, right? So it's not going to give me the same answer. It's actually going to give me 56 meters. So it can't be 8 because you're assuming that it hasn't reached the train when this journey is actually over, right? If we move on to B, it's actually the same, okay? 1/2, the value of A, again, 2, 4, 6, that's actually 6, plus, if we were to add this, again, still 2, 4, 6, 8, 10, right, plus 10, multiplied by the height, which is actually 2, 4, 6, 8, right, multiplied by 8, which is going to be 1/2, okay, or multiplied by the value of 16, multiplied by the value of 8, that's going to be 64 meters, right? So the answer is going to be B, right? So you can continue to work C, right? For example, if you look at C, that's 1/2, okay, multiplied by, that's actually 4, okay, plus, that's actually 2, 4, 6, 8, right? That's actually 8, multiplied by the same height of 8, right? So that's not going to give me the same value because that's just 12 multiplied by 8, okay, which just gives me a value of 48 meters, right? So it can't be C. And if you look at D, again, if you apply the same principle, okay, this is 2, okay, 2, 4, 6, 7, right? Plus, this is again 2, 4, 6, okay, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's again 11 multiplied by the value of 8. That's going to be 1/2, okay, multiplied by 7 plus 11 times 8. That's going to be 72 meters. So it can't be D. It can only be B, right? Very important. Move on to question 8. A stone is released from rest. So this is our stone and it's released from rest. Okay, from rest and let it fall vertically in the air, which graph could show the variation with time of the acceleration of the stone. So initially, the stone is going to fall with acceleration due to gravity, which is A is equals to G, which is equivalent to 9.81. Why? Because the stone has a weight, right? So the weight of the stone is going to be acting downwards. But if the stone begins to fall, air resistance begins to act. So the stone will be falling. Let's assume the stone is here. It will be falling, but acting upwards, we will have air resistance, right? So we have air resistance opposing the motion of the stone. So this will be air resistance acting up. And as the stone continues to move, the speed continues to increase because it's accelerating, right? But the velocity will also increase and the air resistance will also begin to increase because we know that the air resistance is proportional to the velocity squared. As you increase the velocity, the air resistance also begins to increase. And as the air resistance increases, the acceleration will decrease until it's 0 because the weight at one point, the weight down, okay, will be equivalent to the air resistance, okay, that will be acting upwards, right? So when those two things are equal, it means that the acceleration will be 0. So the answer will be D, right? It can't be C. C is when we have no air resistance, right? So this is a graph for no air resistance. A does not mean much. B does not mean much. Okay, very important. Question 9. A slow vehicle and a fast vehicle travel towards each other in a straight line and then they collide. Okay, so, okay, which outcome is never possible regardless of the masses of the vehicles, right? So which outcome can we never get regardless of the masses of the vehicle. So let's look at this, right? We have a slow vehicle, okay? So like this, right? We have two vehicles, vehicle A, okay? So this is vehicle A, and we're going over here, we have vehicle B, okay? So this is vehicle B, right? So this is going to move in this direction, and this is going to move in that direction, right? So they're going to move and then collide, which outcome is never possible regardless of the masses of the vehicles. Let's start with A. Both the vehicles can stop. How is this possible? Right, if the relative, okay, if the relative speed of approach, okay, the relative speed of approach is equal to 0, or momentum before, okay, so momentum before is actually equal to 0, right? It means that before the momentum was actually equal to 0. It means that if they collide, after the collision, the momentum must also be 0. So they can both stop, right? So it can't be A, because there can be a scenario where the momentum of these two vehicles are equal before collision, meaning that after collision, the balls will come to a stop. And this can happen only if relative speed of approach is equivalent to 0, or, okay, or momentum before is actually equal to 0, right? Let's go to B. Only one vehicle stops. Very possible, right? The big vehicle might take all the momentum from the smaller vehicle. They crash, and it's going to, one vehicle is going to stop, and the other vehicle might rebound back, right? So one vehicle might actually stop. Maybe A stops, okay? But B might actually move backwards, right? That's very possible, right? Because momentum will still be conserved, so it can't be B. Let's look at D. The slow vehicle's speed increases. Because of momentum transfer, A is going to exert a force on body B, and B is going to exert a force on body A. But body B is going to transfer momentum to body A. So if they're going to transfer momentum, right, the slow vehicle's speed might actually increase, right? So the slow vehicle's speed might actually increase. So this is very likely, because if the slow vehicle increases because it has gained momentum after that collision, right, it means that the big vehicle, right, the vehicle which was already moving very fast is going to actually be slowed down, but it's going to speed up the vehicle. Maybe this one was moving at 2 meters per second in this direction. This one was moving at 10 meters per second in this direction. When they crash, this will move back maybe with 8 meters per second, right, because it's moving that direction, right? But this still need up to 12. So this one would therefore move with maybe 4, right, 4 meters per second, such that these two can add up to 12, right? Because it's very small, it has little inertia. So it can, the ability for it to be stopped with this motion is very high, so it can easily be just pushed and knocked over the other way, okay? But if you're considering the large vehicle, the vehicle with a higher speed, right, it's very tricky, because for the vehicle's fast speed to increase, it basically means that this has to push this one back. But this one, get this, it's already traveling at 10 meters per second squared, right? Sorry, 10 meters per second, meaning that it has to go back maybe with 12, right? Let's assume that maybe it has to go back with you know, or let's just create a value. Maybe it's going to go back with 11 meters per second, and that has to go with 1 meter per second back. It doesn't make sense, because this is moving so fast, right? So very fast that imagine if a car that's moving so fast in one direction and another car that's moving very slow. How can you say that the vehicle that is moving slow can push the car that is moving fast and cause it to move backwards at an even higher velocity? For me, it doesn't make sense, right? The outcome can never be possible, because, well, even if the mass is so big, the fact that it's moving very, very fast, it can't be even accelerated by a small thing. That thing can be accelerated because it's very small, but it doesn't make sense that the big thing can actually be accelerated at 11 meters per second. So I would say that, you know, the fast vehicle speed increasing, yeah, it might not happen, right? It's very tricky. But the question was quite unclear, but I hope that that makes sense, right? If you have any queries regarding the question, you can put that in comment section below, right? Question 10. Two blocks of masses M and M are joined by a thin string, which passes over a frictionless pulley. Okay, the acceleration of free force is g. What is the acceleration A of the two blocks, right? So how do you tackle these questions? You consider them as two separate systems, right? So consider them, okay, as two separate systems, right? Okay, so the first system is going to be this system that we're going to be dealing with. So because this is a rope, there's going to be tension upwards. Here, there's also going to be tension that's going to be upwards. Considering this ball, we have its weight that is acting downwards and its tension that is acting upwards. So if I say, okay, so if I say the tension subtract, so this is for case 1 for this first ball. So this is case 1. Okay, so if I say tension minus the value of m multiplied by the value of g, this should be equal to my mass multiplied by my acceleration, right? So what I want to find, I want to find the acceleration of these two blocks. So t minus mg, okay, should be equivalent to my mass multiplied by my acceleration. So my value of t should actually be my mass times acceleration plus, okay, plus my mg, right? Plus my m multiplied by g. So this is my first equation 1, okay? Right? So if I'm now considering case 2, the acceleration is downwards, right? Meaning that mg, the weight, is actually greater than the tension. So it's going to be the big M, okay, multiplied minus the tension should be equal to your mass multiplied by your acceleration. So this is the big M, right? So if I say mg, subtract the big M multiplied by A, this should be equivalent to my tension, okay? So this is my equation 2. And I can solve equation in 1 and 2 simultaneously, okay? So it's going to be my mass plus my mg, right? This should be equal to my big mass, mg, minus my big mass, A, okay? So we're going to send everything with m on the one side and everything with without m on the other side. So it's going to be ma, okay, ma plus, okay, the small letter ma, this should be equal to mg, right, the big M, subtract the small letter m and the big letter g, okay, something like this. And here we can factor out a, okay, we'll be left with the big M, okay, plus, right, plus the small letter m, and this should be equal to, okay, if you factor out g here, right, you factor out g, you'll be left with the big M, right, subtract the small letter m, okay? So the value of a therefore will just be m minus m divided by m plus m, right? So this will be my formula for my acceleration, m minus m plus m multiplied by g. So it's m minus m plus m multiplied by g. The answer for number 10 is going to be B. Very important. Now in question 11, the diagram shows a block of copper suspended in water. The block experiences an upthrust from the water. So the upthrust is going to act what? In what direction? The upthrust is going to act upwards, right? Very important. We say that about the basis of this explanation of upthrust is very true. Copper is more dense than water. That doesn't really explain where upthrust is coming from. It being more dense means that it can sink, but that's not the reason why it's having an upthrust. It doesn't make sense. The area of phase R is greater than the area of phase S. Now, it doesn't make sense. That's not related to upthrust at all. The density of water increases with depth. That has nothing to do with upthrust, but the pressure of water increases with depth is very important. Meaning that the pressure at the top here, okay, so the pressure at the top, okay, so the pressure at top is going to be greater, right, is going to be greater than the pressure that will be at the bottom, right? So the pressure that will be at the top is, the pressure that is at the top, so the pressure that is at the top is going to be less because pressure increases with depth, right? There's more liquid at the bottom. It's going to be greater than the pressure, it's going to be less than the pressure at the bottom, right? So the pressure here, right, the pressure at bottom, okay, is going to be greater, right? So since here there's a higher pressure, there's a lower pressure, there'll be a resultant force that will cause it to move upwards. That's what you call upthrust, right? The differences in those pressures results in a force actually beginning to move upwards. So the answer becomes D. Move on to question 12. The diagram shows a solid cube with weight W, sides of length L. It is supported at rest by a frictionless spindle that spins through the center of two opposite faces. One of the faces is shaded. Now the spindle is now removed, so it was once like this. The spin is now removed and it's now placed at a distance of L/4 to the right of the original initial position. Okay, when viewing this the shaded face, what is the torque of the couple that would now be needed to keep the cube at rest? Okay, so to keep this thing at rest, we have to oppose what is already there, right? That's how you can keep something at rest. So first find out what is already going on, right? So you have a mass here that is acting downwards of the spindle itself, right? This is your mg, okay? And the value of your distance here is actually L/4, okay? And this is going to act in this direction, right? This is basically the anti-clockwise direction, right? Because it's going to act in that direction. If you've seen a watch, right? If your watch sweeps in that way, that's clockwise, right? It's like 1 a.m., 2 a.m., 3 a.m. If your watch was to sweep in the other direction, right, that would be anti-clockwise. So basically, for me to find the clockwise moment, I know that torque is equivalent to my force multiplied by my distance, right? Which is going to be W multiplied by L/4. But this is going to be anti-clockwise. So if I want to keep this in equilibrium, what do I need to do? I need to apply WL/2, but I need to apply it, right, clockwise. So it's WL/4, right? So I need to apply WL/4, but now it's going to be clockwise. Because if it's WL/4 anti-clockwise, I just need WL/4 anti-clockwise for me to be able to turn it. So it's just a bit tricky, but just understand that if it's going to cause a moment anti-clockwise of L/4 times W, I need the opposite moment clockwise for me to counteract it. Very important. Okay, move on to question 13. A street lamp is fixed by a wall, okay, of a metal rod and a cable, right, which vector triangle could represent the forces acting at point P. The forces acting at point P. So basically, we're going to have the value of this thing that's going to be acting down, right, because of weight at P. We're going to have the weight that will be acting downwards, right? The weight that will be acting down. So it can't be A because it's acting up, and it can't be C because it's also acting up, right? But we're going to have tension in this cable, right? Tension in this cable, that will be over there, right? And that tension in this cable is going to actually be moving in this direction, right? So the tension is going to move in this particular direction itself, right? So the tension is going to be pointing up, so it can't be B because the tension here is pointing down, so the tension has to be pointing up, right? And the last remaining force, right, we have to create a closed triangle, and the last remaining force will actually be acting downwards in that direction, actually pushing in that direction itself, right? Meaning that at this contact point, there will be another force that will be acting in that direction, right? Because since that tension is pushing in that direction, that tension is going to have two components, right? The tension that's going to be acting up, tension acting in that direction. So this is going to help the force also that will be here, right? So these two forces will be helping each other overcome the tension, but the tension will be very big, that will be acting in the opposite direction. So very important for you to be thinking of that. Okay, so that explains it. There must be a horizontal force that keeps everything. So there must be a horizontal force there that keeps everything in equilibrium, which explains this force that will be acting in this particular direction, right? But basically, you're supposed to know that if you identify the weight acting down and the tension acting that direction, your answer would definitely be D, because those two would eliminate every single answer. Okay, very important. Move on to question 14. Two rigid beams, X and Y and Z, are fixed at their lower ends. So they're fixed here and they're fixed over there. And each beam is inclined at 50 degrees to the horizontal, as shown, right? And the weight of 4 newtons times 4 times 10 to the power of 4 newtons hangs from Y, right? The whole structure is in equilibrium. What is the force exerted by each beam on the hinge, right, at Y? Okay, so basically, the force that is going to be exerted on each beam at the hinge by Y is that this beam, okay, so if we're considering beam XY, it's going to push beam YZ like this, right? But as it pushes YZ like this, YZ is going to exert an equal and opposite force that is going to move upwards, okay, something like this, right? And YZ is also going to exert a force down on actually this rod itself. but this is going to react and it's going to create a force that will be moving in this direction, upwards. So I can basically just consider these two forces and eliminate these ones and just consider these two forces as my only forces acting, right? But they just going to be the same. This is the force exerted by each beam on the hinge at Y. The force that this exerts down at the hinge and the force that this exerts down on the hinge, they both create reactions, right? So if I resolve these two forces, this force that would then be acting up should cancel the force that is acting down, such that the resultant force is 0, okay? But since I have 50 degrees over here, if I were to position this and draw a horizontal line over here, right? If this is 50 degrees, okay, this is going to be 40 degrees, right? So that's going to be 40. So since this is going to be F, right? That's going to be F cos 40. So it's going to be F cos 40. But there are two of them, right? Contributing. One is contributing in that direction and the other is contributing in that direction, right? So they're going to be two of them. That's going to be equal to 4 times 10 to the power 4. Right? So the value of F will be 4 times 10 to the power 4 divided by 2 times cos 40. Right? So that's going to be our value of F. If you have 4 times 10 to the power 4 and divide times 2 times cos to the power 40, we'll be able to get an answer of about 26,108 newtons, which is about 2.6, okay, which is going to be A. Right? So 14, the value is going to be A, which is going to be about 2.6 times 10 to the power 4 newtons. So how are you supposed to think about this? Well, you're supposed to look at the forces that are acting themselves and say, this is going to exert a force down on the hinge, XY, is going to exert a force down on YZ, but YZ will exert an equal force, react, that is going to act up. And XYZ is going to exert a force on X, right, on YX, and YX is going to react, exerting a force up. So those two forces will be equal in magnitude. If you resolve them, they're going to create a resultant force that's going to be equal to the force acting down. So this whole thing is in equilibrium because this weight that is acting down, okay, needs something that's going to counteract it so that it can be stable. Okay. Moving to question 15. A is trapped inside a glass bubble which is immersed in water. Okay. So this A is trapped, right? It's trapped inside this gas bubble. Okay, so this is our A. And from the question, the density of water we've been given as rho W and rho M. The surface of water is open to the atmosphere over here. We've been asked what is the pressure of gas of the air in the glass bulb. Okay, so what do? We identify a point, right? This is our point of reference, right? This is our frame of reference, right? So the pressure on the left, since it's equilibrium, the pressure will be equal at this point, right? Okay, so the pressure will be equal at this particular point. What I mean it will be equal? The pressure on this side will be equal to the pressure on that other side. Okay, so if we look at this pressure which is open to the air, this is basically, so this is open to atmospheric pressure plus the density of water. Look at this. This is HW, right? Meaning that this is also HW, right? This is just HW. So the density at that point is going to be, right, HW. So it's rho of water multiplied by G multiplied by H of W, but plus the air due to the pressure, because there's going to be atmospheric pressure also acting down. There's the whole atmosphere above that's pushing down the water. So it's going to be pressure due to the water plus pressure due to the atmosphere. And it's going to be equal to, let's move on to the other side, with pressure of this air, which is pressure of this air, plus the small little pressure due to the mercury that is there, right? So this small little pressure that is due to the mercury that is there, right? So how do I find that? This is HM, okay? Density of mercury is rho M. So it's rho M, okay? HM multiplied by the value of G. So my pressure of air is now going to be rho W multiplied by G multiplied by HW plus my pressure subtract rho M HM multiplied by G, right? And that's going to be B. Okay, so as you think about this, when you're at the same level, the pressure is going to be the same at that level. So it's just a matter of you find the pressure on the left, pressure on the right, equate the two and find the answer that you want. Okay. Move on to question 16. A ball of mass M is thrown up to height h in air with an initial velocity of u. What is the total work done by the gravitational force on the flight during its flight from P to Q? So basically, The total work done by the gravitational force is that the gravitational force is going to increase until it reaches this particular point, right? So the work done is now increasing this thing as we've risen it up to this particular point, let's say X, right? But this thing is going to decrease until it hits Q. As it hits Q, it has lost all its gravitational potential energy. So the total work that you've done is going to be 0, right? Because comparing P and Q, okay, has it risen actually from the ground? It has not. Has the gravitational force done any work? Honestly, it has not. Because going up was mgh, going down you've lost mgh, so the final will be 0. So it's actually mg, okay, so it's actually mg h2 minus h1. What is h2? h2 is 0. Initially your height is 0, right? Your final height will therefore be 0. So you change in GPE, right? It's just going to be 0. Okay, move on to question 17. What is the ratio? So we're given a constant force F acting on the car of mass m, okay, through a distance of s, and constant velocity v. The angle of the slope is alpha. What is the ratio of the gravitational potential energy gained by the car over the work done by force F? So force F does work in doing this particular thing from F up until S. So what does force F do? It's actually going to be F multiplied by S, right? So it's going to be Fs. Okay, but considering the gravitational potential energy gained by the car itself, right? So let's consider the center of mass of the car. Initially, it was here. This is where the center of mass of the car was, right? So if we were to move it here, right, it's now at this particular position, right? So it has actually gained height from this point, right? This is the height, h, that we're talking about, right? But this is still the same, right? From here to here is the same as s, because from here to here, it's just the same, because I've removed this part and I've added it over there, right? So it's just that same value of s, right? So this mg sine theta, okay, so here is the gravitational potential gained by the car. The car actually had a weight mg, okay, but the mg itself has risen because now it's here, right? The mg is done work, which is going to be mg, okay, multiplied by, remember, this is s sine alpha, s sine of alpha, okay, but this is the same as that. They can cancel out, and I'll basically be left with, okay, mg sine of alpha divided by f, which is going to be d. Very important. Question 18. Car X is traveling at half the speed of car Y. Car X has twice the mass of car Y. You know what? They want us to find the statement which is correct, okay? Create values, right? This is the questions with these questions, right? This is the trick with these questions. Create your own values, right? So let's have car X, okay, a fictional car, and say this is car X, okay? And then we say this is car Y, right? And then this is car X, and then this is car Y. As you can see, car Y and car X is moving, but it's moving at a speed that is half that of car Y. So let's say it's moving at 2 meters per second, meaning car Y is moving at what? 4 meters per second. So we're done with speed, right? We move on to mass, okay? If we move on to mass, car X is moving at twice the mass of car Y. So car X has actually 4 kgs, okay? And car Y is actually 2 kg. So let's go on and find the kinetic energy. So EK, okay, for car X is going to be 1/2 the mass of car X. For the speed is going to be 2 squared, right? It's going to be 1/2 multiplied by 4 multiplied by 2 squared, which is going to be 8, right? 8 joules. Okay, let's go for car Y. EK for car Y is going to be 1/2 the mass of car Y is 2, and that's 4 squared, which is going to be, okay, 1/2 times 2 times 4 squared. That's going to give us 16. So as you can see, the speed, the kinetic energy for car, okay, for car X is actually half, right? So for car X is half that of car Y. So car X is actually half the kinetic energy of car Y, and the answer is A. So I highly recommend whenever you see questions, use actual figures. That makes it so much easier. Instead of using the equations, rearranging them, trying to link and find the connections, just assign values to these things, right? And it will make your life so much easier. Move on to question 19. During refueling, a petrol receives 50 liters of in 90 seconds, right? The petrol has 34 millijoules of energy per liter, okay? For an electric car to receive the same amount of energy in the same time from a 230 volt supply, what is the minimum current that is required? Okay, just, write all the equations that you know. We know that V is equal to the work done per unit charge, but I know that Q is actually equivalent to IT. So I can therefore say V is actually work done multiplied by IT. So the value of V multiplied by I multiplied by T is actually going to be equivalent to my work done, right? Multiplied by I multiplied by T is going to be actually equivalent to the work that I have actually done. So if I'm to consider this, the value of I is now going to be the work done divided by the value of V multiplied by the time that you took. But what did you do? What is your work? If we have 34 millijoules per liter, that's going to be 34 times 10 to the power of 6. How many liters do you have? You have 50 liters. What is the time? 90 seconds. What is the value of V? 230. So if you're to compute this, you're going to find the current that that is going to be supplied, which is actually going to be the minimum current that's going to be supplied. So you're going to get something like, okay, you're going to get something like 82,125.60386, right? That's going to be about 82, right? And that's going to be 8.2 times 10 to the power 4 amperes, right? So it's going to be B. Very important. Move on to question 20. A boat is subjected to a tensile force F. Okay, so this is our boat. The boat is a circular cross-sectional area. Okay, and at end D, the diameter is 2D. Okay, so basically it's like circular, more like that, right? And it's also circular at this particular end. And we're told that the diameter of this end is 2D, and the diameter at that end is actually D. What is the ratio of stress at Y over stress at X? What do we know? We know that stress, okay, is actually the force divided by the area. Okay, so stress at X, so stress X over stress at Y, you're just going to need the force that is at X divided by the area that is at X over the force that is at Y divided by the area that is also at Y, right? So that's basically what you're going to need. And we know that force, the area will be pi d squared divided by 4 divided by F over pi d squared divided by 4. So basically this is going to be 4F, okay, over pi d squared, right? But this is for X multiplied by pi, that is dy for Y, over 4 multiplied by F. But these things are going to experience the same tensile force. But what's different is end X as a diameter of 2D. But the tensile force is basically the same, meaning that this is essentially the same. Okay, so for F, this is basically the same. Okay, so they cancel out, pi cancel out. Okay, we're basically left with dy squared over dx squared, right? But dy, remember, it's just d squared. But dx is actually 2d squared, right? So that's going to give you d squared over 4. D squared, those two cancel out, we'll be left with 0.25. But the question it said, okay, so the question it said stress of, so I have stress of X over Y, which is 0.25. But my question is said stress of Y over stress at X. Okay, so basically, if stress, okay, so if stress at X over Y is actually 1 over 4, okay, so I wake this in reverse, but it's still fine. That would be 4. Stress at X is equivalent to stress at Y. Therefore, stress of X, so stress of Y over stress at X is basically going to be 4, right? So the answer is going to be D. So it's very important for you to figure it out, right? Stress at Y is force at Y over area at Y, right? I just done it in reverse. I'd find X over Y, right? But, just find stress at Y, you divide by the stress at X, and you can be able to find your answer. Very important. A rectangular block, okay? Move on to question 21. A rectangular block of steel can support a very large component of a bridge that is a height of 15 centimeters, right? Okay, so let's draw a diagram, right? So if a steel, right, which is a rectangular block that is designed to hold a bridge that is a height of 15, right? So it's more like that, okay? And the height is actually 15 centimeters, right? So that is taken care of, okay? The cross-section area is actually 20 times 12, okay? And it is designed to compress, so X is designed to be 1 millimeter. What is the maximum load that it can support given that Young modulus? Okay, so very important. So we know that the Young modulus is basically the ratio of stress to strain. Okay, but stress is basically the force divided by the area, okay? And strain is basically the extension, okay? The extension divided by the original length, okay? So our Young modulus can therefore be expressed as F over A divided by X over L, which is going to be FL over AX, right? So that's going to be my Young modulus. But my Young modulus is what? 2.0 times 10 to the power of 11 multiplied by my area, which is 20, okay, times 12, times 10 to the power of negative, which is negative 2 squared, okay? That's for that, multiplied by my extension, which is 1 millimeter, 1 times 10 to the power of negative 3. And I divide all of that by 15 centimeters, so it says by 15 times 10 to the power of negative 2. So if I compute this, I should be able to get my value of, the minimum load that I require. So it's just a matter of you being able to apply it and say, what is the Young modulus you're trying to find? What is it that you're given? And how do you just plug in that information, right? So the height we were given, and we're given everything from the area, and it's just a matter of us finding the Young modulus. So it's going to give me about 32, okay? 32, 1, 2, 3, 4, 5, 6. Okay, and if I divide this is going to just be 32. If I divide by 10 to the power of 6, right, by 10 to the power of 6, it's basically going to be 32 mega newtons, right? 32 mega newtons, which is going to be A. Okay, move on to question 23. Question 22. When sound travels through air, the air particles vibrate. A graph of displacement against time for a single air particle is shown, which graph base shows how the kinetic energy of the air particles varies with the time. Okay, so get this. The gradient of a displacement time graph, okay, so the gradient, okay, of a displacement time graph is actually equivalent to my velocity. Okay, that is something that is very instrumental, right? And then we know that if you can draw a horizontal line, the gradient is 0 at that point. So if I go here, initially my gradient is 0. So I expect my kinetic energy to start from 0. Right? So EK should be 0 here. Right? This is 2, 3, 4, 5. So I expect 5 points. So I expect 5 points where EK is going to be equal to 0. Why EK is equal to 0? Because kinetic energy is actually 1/2 multiplied by the mass multiplied by the velocity squared. So if this guy is 0, it means that the whole expression tends to become 0. Just because the velocity is 0, right? So I need 5 points where my velocity is 0. Let's go. For this one, I have 1, 2, it can't be A. 1, 2, 3, it can't be B. 1, 2, 3, 4, it can't be C. But here, 1, 2, 3, 4, 5. So the answer has to be D. Very, very important, okay? Move on to question 23. Which wave is a longitudinal wave, right? Which wave is a longitudinal wave? So a longitudinal wave, light wave, that's an EMF wave. And EMF waves are basically transverse in nature. Okay, so they're basically transverse in nature. So it can't be a light wave. Radio wave, that's an EMF again. That's out. Ripple on the surface of water. Water waves are basically transverse waves. So they're out. And the sound wave is the only longitudinal wave that exists. Okay. Question 24. A vibrating tuning fork is held above a glass cylinder filled to the top with water. The water level is steadily lowered. A loud sound is first heard when the water level is 83.5 centimeters. So how do you hear loud sound? You hear loud sound whenever you form a stationary wave. So if you're at this point, the first stationary wave that you can form will be like that. Okay, so where we have a node at this point here, and you have an antinode at that point, right? So that's what we've been told. The second next loud sound is heard when the water level is at 17.1. So the next one you heard when it's now at 17. So it'll be again something like this. That is where you're going to hear the next wave at this point, right? But get this is a node and that is a node, right? So the differences in these two heights is actually the distance from a node to reach another node, right? So if you find that distance, we found the distance from this node up to that particular node, right? So from node to node, the distance is going to be 83.5 subtract 17.1. So if you find this difference, it's going to be our distance from node to that node, which is going to be 66.4 centimeters. But we know that from a node to a node, this is actually half lambda. So half lambda is actually 66.4. So the value of lambda is going to be that value multiplied by 2, which is going to be 132.8. Divide that by 100, you get about 1.328 meters as your value of lambda. So we want the frequency. We know that, but okay, we know that V is equals to F lambda. So the value of F is going to be V over our value of lambda, and the value of F is 340. Okay, so it's 340 divided by 1.328. So once you compute this, we'll be able to find our frequency. So we find our frequency as approximately 256.0240 hertz, right? So about 256 hertz, and the answer is going to be B. Move on to question 25. Okay, a train that is moving in a straight line along a railway track has a whistle that continuously emits sound of frequency F. A woman standing by the side of the track hears sound of frequency 0.85 F. The speed of the sound is 340 meters. What is the velocity of the train? So this is basically a question on Doppler's law, Doppler effect, Doppler effect, you know that the observed frequency is actually equal to the actual frequency, okay, V over V, but since it's less, 0.85 means it's less than the actual frequency, it's moving away. So I need to add that particular value of V, right? Because it's moving away, okay? Because it's actually less, so it can't be B, it can't be D, because it's actually moving away, okay? Okay, so we want to find the value of that velocity, right? So what do we do here? The initial velocity that the person is having is going to be F, right? The initial velocity that the whistle of the railway is actually sounding is F, and that velocity is 0.85, right? And the speed is actually 340, and that's 340 plus V. And we want to find that value, that Vs, the value that the train is actually moving. But it's away, remember, because the velocity is actually less, okay? So we have 0.85 multiplied by 340 plus Vs, that's going to be 340 F. Okay, so something like this, right? So if you have 0.85 multiplied by 340, right, that's going to give about 289 F plus 0.85 FVS, right? There's going to be 340 F. So 0.85, okay, so 0.85 FVS multiplied by 340 F minus 289 F, right? So Vs is basically going to be 340 minus 289, okay, multiplied by F divided by 0.85 multiplied by F. So your value of Vs is just going to be 340 minus 289 divided by, so it's 340 minus 289, okay, divided by 0.85, divided by 0.85. That's going to give you a value of about 60. So it's going to be 60, but it's going to be away from the woman. So your answer is going to be C. Very important. Orange light in vacuum has a wavelength of 600 nanometers. What is the frequency of this light? Orange light is, my friends, orange light is actually an EMF wave, okay? We've been saying this. We know that V is actually F lambda. So the value of f will be your value of v, 3 times 10 to the power of 8, divided by the wavelength, which is 600, times 10 to the power of negative 9. Okay, so that's going to give us the value of our frequency. So we already know that EMF wave travel at a very fixed speed, which is 3 times 10 to the power of 8. So that's going to give us 5.0 times 10 to the power of 14 hertz. So the answer is going to be D. Move on to question 27. A stationary wave has a series of nodes. The distance between the first and the sixth node is 30 centimeters. What is the wavelength of the sound? So just draw the diagram. You have the first node, the second node, the third, fourth, fifth, and sixth. And the distance is actually 3 centimeters. So to go from here to here, right? So to go from here to here, it's actually going to be 3 centimeters, right? So here to here, this is lambda. From here to here, this is lambda. From here to here, this is half lambda. So basically, 2.5 lambda is actually equivalent to what? To 30 centimeters, right? So it's actually equivalent to 30 centimeters. So this is basically 2.5 lambda is actually 5 over 2 lambda. That's the one which is equivalent to 30 centimeters. So the value of lambda is going to be 30 times 2, okay, divided by 5. 30 times 2, that's 60. Divided by 5, that's 12. So it's going to be 12 centimeters, which is going to be D. Very important. Move on to question 28. Which diagram shows diffraction of water waves in a Ripple tank? A is not diffraction. Diffraction is the spreading of waves into the geometric shadow. How is this diffraction? The wave is just getting smaller as it enters through. It doesn't make sense. It can't be A. B, this only happens if the gap is very, very, very big, right? So let's assume that for this to be correct, obviously B is wrong, but it's correct under this circumstance, provided that, so let's remove this, provided that the gap was something like this. Okay, something like this. This was the only situation that this wave was going to be diffracted, that because the amount of diffraction decreases the bigger the wave gets, right? So it's not that because it's very, very small. But if you look at C, this is very perfect, right? The wave comes in, it gets diffracted, spreads into the geometric shadow. This is the geometric shadow. Okay, it spreads into that shadow, right? But if you look at D, that doesn't even make sense, right? How is that? Like the wave comes in, now it's reversed. It's not adding up, right? This doesn't make sense. Okay, so the answer is going to be C. Move on to question 29. A hill stands between a radio transmitter and a house. The radio transmitter cannot be seen from the house, but radio waves from the transmitter are received as the house. So radio waves are going to do like this. They're going to be transmitted, then they're going to diffract. Okay, after they diffract, they're going to reach the house, right? So let's start. They cannot be seen, but the radio wave from the transmitter is received, right? So let's go. The wavelength of light is longer than the wavelength of radio waves. What do we know? We know that using this abbreviation, okay, the wavelength actually decreases, right? So the wavelength of light, right? The wavelength of light, which is over here, visible light, is actually less than that of radio, right? This is more. So meaning that A is wrong and C it's A and the wavelength of light is shorter than the wavelength of radio waves. That's true. The wavelength of radio waves is longer than the radio. That's true. The wavelength of radio waves is shorter, so it's A and D that are wrong, right? So because of the first statement, which is ending here, right? It makes A, okay? It makes A and B, A and D actually wrong, right? But considering B and C, we're left with these statements that are over here, right? There is going to be more diffraction, actually. There's going to be more diffraction. Why? Because since the wavelength is very, very big and the hill is extremely big, for there to be maximum diffraction, they have to be almost equal. So the wavelength of the wave, the radio wave, as it passes through the hill, is going to get diffracted because it's passing through an edge, right? As it passes through this edge, it's going to start getting diffracted, and it's going to be very maximum because the wavelength of radio light or radio waves is actually much greater than that of visible light. Very important. Move on to question 30. In an experiment to demonstrate the double slit experiment, using light, the distance from the slit to the screen is doubled and the slit separation is halved, but the wavelength is kept constant. By which factor does the separation of the adjacent bright fringes change? Okay, so we know that lambda, is really equivalent to AX divided by D. Okay, guys, I would highly recommend that just make up values, right? So that is much easier. Instead of just looking at the ratios, how are they changing, just say lambda is equivalent to 2, A is equivalent to 3, D is equivalent to 4. Okay, so for case 1, X is going to be lambda times D divided by A. Lambda is 2, your D is 4, you divide that by 3, you get your value of 2 times 4, okay, divided by 3, you get 8 over 3, which is your value of X, right? You go on to case 2. What have been told for case 2? We've been told that the wavelength is kept constant. So for case 2, X is equals to lambda D over A, okay, where lambda is now going to remain 2, but A and D are going to change, right? So the value of A, we've been told that the slit separation is halved. It was once 3, now it's going to be 3 over 2. The value of D is doubled. It was once 4, now it's going to be 8. So let's just find the value of X, right? So the value of X is going to be 2 times 8 divided by 3 over 2. Okay, so it's going to be 2 times 8 divided by 1.5. It's going to be 32 divided by 3. So how do you find the factor by which it has changed? To find the factor, it's going to be the final X divided by the initial value of X. So it's going to be 32 over 3 divided by 8 over 3, which is going to be 32 over 3 times 3 over 8. Those cancel out. 32 divided by 8, okay, 32 divided by 8, that's going to be 4. So the answer is going to be 4, which is going to be D. So guys, I highly recommend whenever you see questions that have halving of things, doubling of them, make up your own values. You always get these ratios correct if you work it like that. I created my first case, then I created my second case because of that. Question 31. This is this is an electric fields question. Okay, we no longer do electric fields, they're no longer in our syllabus. It's just question 32. So we start with question 33. Two copper wires are joined together and they carry a current as shown. Okay, wire P has a diameter of D and wire Q has a diameter of 2D. What is the ratio of the average drift velocity in P and the average drift velocity in Q? What do? We know that they're going to have the same current basically because these are connected in series, right? And I know that I, okay, is equals to N times A times V times Q, okay? And this is going to be the same, guys, meaning that if I say NP, okay, multiplied by AP, multiplied by VP, multiplied by Q would be equivalent to, right? If I were to find for Q, it's going to be NQ multiplied by AQ multiplied by VQ multiplied by Q. Okay, and I want to find the ratio in P over the ratio in Q. So what I want to find? I want to find VP divided by what? Divided by VQ. So that's basically going to be, based on the ratios that I've created, is going to be NQ times AQ times Q divided by, on the denominator, I'm going to have NP multiplied by AP multiplied by Q. And these two are going to cancel out, this and this, that and that. And I'll be left with V, okay? VP over VQ is actually going to be equivalent to AQ over, okay, so it's AQ, right, over AP, okay? But this is also equivalent to, we know that area is going to be pi, okay, dq squared over 4, right? The area of P is going to be just pi r squared, right? Pi r squared and d over 2 squared, right? That's why it's pi d squared over 4. So it's going to be, this is going to be pi dp squared divided by 4. Okay, I'm starting over here, right? So this is now going to be, okay, so once I have this particular expression laid out, so let's write it clearly. This is going to be pi dq squared divided by 4, okay, multiplied by 4 over pi dp squared, right? So these 4 are going to cancel out, okay, that 4 and that 4, that pi and that pi are going to cancel out, and I'll be left with Vp, okay, over Vq actually being equivalent to dq squared, okay, so it's dq squared over dp squared, right, over dp squared, which is going to be, but dq is actually 2d, right, so that's going to be 2d squared, right, divided by dp, which is actually going to be d squared, right, so that's going to be 4, actually 4d squared divided by d squared over there, right, so those two are going to cancel out because they are the same, right, so that's going to give you an answer of 4, right, so your answer is going to be 4, which is D. Very important. So we only knew that I is equal to NAVQ, right, and we created those two expressions and we just found the value of Vp divided by the value of Vq. Okay, move on to question 34. A cell of negligible internal resistance is connected to a resistor R1, R2, and R3. The cell produces a power to the circuit and power is dissipated in the resistor. Which equation must be correct? Power lost in R1, okay, is equal to power lost in R2 and power lost in R3. It's very different, right? The resistance might be different, right? The voltage might be the same. Remember, we know that V squared might be V squared over R is actually equivalent to my power, right? But we don't know the resistance of R1. It might not even be the same because it's a matter of gambling with these ratios, right? You're actually going to tell me that 1 over, because it's V squared over R1 is equivalent to V squared over R2 is plus V squared over R3. But we don't know that. We don't know if the ratios, what exactly is 1 over R, because everything is unclear, right? But the question is saying must be correct, meaning under any circumstance, that relationship must be correct. We don't know that, right? So A doesn't make sense. Power loss in R2 is equivalent to power loss in R3. What if, again, they have different resistances? They have the same current, but we know that P will be equivalent to I squared R. Same current, but the resistances are different. So power loss will not be the same. So B is wrong. Power output of the cell will be equivalent to power loss in R1, power loss in R2, and power loss in R3. That's very correct. Because, get this, the power output basically refers to the energy that I actually have from my whole cell. And that will be equal to all the energy that I give to all these particular things. And that's actually Kirchoff's second law, right? So it's very important for you to think of these things. So C will be correct. But D will be wrong because the power output of the cell is not equal to power loss in R1. Okay, so the answer is going to be C. Move on to question 35, which gradient shows a metallic conductor. So the metallic conductor is A. And as you can see over here, those are some of the graphs that you need for IV graphs, basically for IV graphs and for all those things. But this question said the resistance is given by the gradient of the graph. And you know that resistance is actually V over I. And it makes this one correct because D is actually I over V. And this doesn't mean anything. This actually means 1 over R, right? Okay. Move on to question 36. A typical mobile phone has an EMF of 5 volts and internal resistance of 200 mega ohms. What is the terminal PD of the battery when it supplies a current of 500 milliamps? Okay. We know that, okay, E is equals to V lost plus V terminal. Okay, that's very important. Since V lost is, the EMF is 5, V lost is going to be 200 times 10 to the power of negative 3 multiplied by the current. Okay, that's the resistance multiplied by the current, which is 500 times 10 to the power of negative 3 plus your value of V terminal. Okay, so 5 subtract, right? So if you say 200 times 10 to the power of negative 3 and multiplying that by 500 times 10 to the power of negative 3, that's going to give us 0.1. That must be equivalent to our V terminal. So our V terminal is going to be equivalent to 4.9 volts, right? So 4.9 is usually going to be B. Okay, move on to question 37. The circuit shown contains a resistor S. Okay, so it's neither in series nor in parallel with the other resistors. Okay, Kirchoff's laws can be used with the data in the diagram to deduce the resistance of each of the two identical resistors labeled R. So how do we use Kirchoff's laws, right? We have Kirchoff's first law, okay, which talks of current. how current entering into a junction is equal to the sum of current leaving that junction, okay? Kirchoff's second law is interested in EMF, right? The EMF across a closed loop is equivalent to the EMF from the source itself, right? So let's first start with those laws. If I arrive at this junction, if I have 3 here, I should have 1 amp over here, right? That is my 1 amp that I'm moving over here. If I arrive at this junction, if I have 1 there and 0.5 there, I should have 1.5 amp that will be over there, right? That's Kirchoff's first law. With Kirchoff's second law, you identify a closed loop, right? This outer loop is going to be my loop, okay? That is what I'm going to be dealing with. So I can remove everything over here, right? Because I want to find the resistance in R. So I can remove everything over here and make my circuit be like this, right? So this is going to be my new circuit that I'm going to be dealing with, right? And I know that going over here, this is going to also be 4 amps, right? So let's first start. I have 12, right, on this side, and it's going to be equivalent to that 4, okay? That would take 0.5, okay? Plus, that's 1 and that's R. So it's 1 multiplied by R, okay? Plus, that's 1.5 multiplied by R, okay? That's going to be 12. Is going to be equivalent to 4, okay, times 0.5, that's actually 2, plus 1 plus 1.5, right? So 1 plus 1.5 is actually going to give us 2.5 R. So 2.5 R is actually going to be equivalent to 12. So R would be 12 minus 2 divided by 2.5. So the value of R is actually going to be 4 ohms, which is actually going to be B. So you had to use Kirchoff's laws in 2 ways. Number 1, we use it to determine the currents that are actually appearing in that circuit and the current appearing in the other circuit. That was Kirchoff's first law, right? Currents branches when it arrives at the terminal. The second one, I used it in identifying my closed loop. I identified my closed loop and I removed everything else, and I was just left with that closed loop on its own, right? Move on to question 38. Which range of voltages can be obtained between X and Y? We're given a potential divider that is connected to a 12-volt supply of negligible internal resistance, okay? So I want to find the range of voltages that can be obtained between X and Y. So basically I can move this around, right? Remember, like I always say with potentiometers, move them to the 2 maximum positions. So if I remove it here, I can basically move it over here, right? Here, I actually get 0 because there's nothing in between. This is 0, right? So it starts from 0, 0, and 0, and 0. So I can't eliminate anything based on that fact. Okay, but I can move it over here, right? I can remove it and actually move it where it actually is, right? When it's here, it is exposed to the full 100 ohms that are there. So for me to find the PD across that would be 100 divided by 100 plus 300 multiplied by 12. So if it's 100 divided by 400 multiplied by 12, that's actually going to be 3 volts, right? So my current is going to range from 0 up until 3 volts, right? So it's very important for you to be thinking about those equations, okay? Question 39. The diagram shows a sequence of radioactive decays involving 3 alpha particles and 1 beta negative particle. What is nuclide T? Okay, so let's start. So nuclide T is going to have 2, 37, 93, and P. Okay, so let's start over here. Okay, so basically, an alpha particle, right, has a mass of 4. So that's 4 and that is 2. Okay, that's 0 and that's -1. That's 4 and that's 2. That's 4 again and that's 2. Okay, so that's 4 there, right? That's 4 there and that's 2 over there. Okay, so if I remove 4, so I'm going to remove this Q and I'm going to form an isotope that is 237 minus 4. So it's going to have 233, okay, and it's going to have 93 minus 2, which is going to be 91, which is going to be Q. And that Q is going to lose something, and then it's going to form R. So it's going to lose -1, so I'm going to add 1 because it's going to lose a neutron that's going to turn into a proton, right? So this is going to be 233, and that's going to be 92, that's going to be R. Okay, that's going to be our value of R, okay, over here, right? And we're also going to lose an alpha particle, okay? So after losing an alpha particle, this value of S will disappear. So after the value of S disappears, we're going to lose 233. We're going to lose again another 4. We're going to be left with 229. Okay, from 92, we're going to lose 2. We're going to be left with 90. This is going to be S. And lastly, if we lose again another 4 and another 2, so that's going to be from 229, that's going to be 227, and that's going to be 90, so that's going to be 88, right? So that's going to be 88, okay? And that's going to be T. So it's 88 and 227, 88 and 229 minus 4, that's going to be 225, okay? Cut here. 229 minus 4, again, that's going to be 225. 90 minus 2 is going to be 88. So it's 225 and 88. 225 and 88. The answer is going to be A. Okay, so the answer is going to be A. Move on to question 40. Which combination of up and down quarks form a neutron? So basically, a neutron is made up of a down quark, and an up quark. So it has to be down quark, and an up quark. So our answer is C. Okay. So thank you guys for watching. This is the end of my video. I hope you find it very useful. If you like the paper, I'm going to post it in my comment in the comment section below, or you're going to see it in my description. So if you want to view the paper, you can easily download it and be able to access it. If there are any queries or any comments, really, just put in the comment section and I'll be able to address it. Thank you guys for watching. I'll see you in the next one.